Burning up with curiosity? Let's cool off with conduction and convection secrets. This video takes a closer look at systems where conduction and convection work hand in hand. Examples from the real world include high-performance systems such as nuclear fuel rods and heat exchangers, air-cooled engines and braking components as mechanical systems, thermal management devices like electronic heat sinks and insulated steam pipes, and manufacturing applications such as injection molding equipment. To make sense of these systems, we often study fins, simple structures with surprisingly rich thermal behavior. Fins, also known as extended surfaces, are added to a system to enhance heat transfer. To understand why, let's start with a simple plane surface. Heat conducts to the surface from the interior and is then removed by convection, which we quantify using Newton's law of cooling. Now, if we want to boost the rate of heat loss, we have two main options: increase the convective heat transfer coefficient, H, or increase the available surface area, A. In many practical situations, especially those involving air or natural convection, increasing H is difficult or inefficient. That's where fins come in. They provide a passive, cost-effective way to enhance cooling by increasing the surface area, without the need for additional energy input. Extended surfaces are often arranged into what we call heat sinks. These come in many forms, like rectangular fins, annular fins wrapped around pipes or high-power cables, or pin-type arrays, each designed to balance performance, cost, and ease of manufacturing. Let's now take a closer look at a basic heat sink design, consisting of uniformly spaced cylindrical fins with constant cross-section. These fins are mounted on a base area at temperature, Tb, and the array is exposed to ambient air at temperature, T infinity. As a first approximation, we often assume the fins are spaced far enough apart to avoid mutual interference, leading to a uniform heat transfer coefficient. The fins are also considered slender, so their cross-sections remain nearly isothermal. Each fin contributes a surface area, A fin, for heat transfer, while the exposed base area, A on fin, still contributes as well. Overall, the extended area greatly exceeds that of the plane base. But to ensure this actually improves cooling, the fins must be made from a material with high thermal conductivity. To make sure a heat sink like this performs as intended, we need to understand how heat transfers from the fins themselves. That way, we can accurately quantify the total heat flow from the entire system. Let's consider a single fin made from a material with thermal conductivity K, length L, cross-sectional area AC, and perimeter P. Heat enters the fin at the base and conducts along its length, while being lost to the surrounding air by convection. As a result, the temperature decreases gradually along the fin, typically in a monotonic fashion. To predict this temperature profile, we use what's known as the fin equation. This comes from applying a differential energy balance along a small element of the fin. It's interesting to observe when derivation of the fin equation comes up, students nod thoughtfully, murmuring, "Oh, yeah, totally get it," while mentally outsourcing the derivation to the maths boffin. Like they are subcontracting a plumbing job. But don't worry, we'll skip the derivation. In solving the fin equation, we define theta as the excess temperature above ambient, and introduce a parameter m, which depends on the fin's geometry and material properties. Since the fin equation is a second-order differential equation, we need two boundary conditions. At the base, the temperature Tb is known. And for this case, a long fin, we assume the excess temperature drops to zero at the tip. Solving under these conditions gives a surprisingly simple expression for the temperature profile. Now, we want to calculate how much heat each fin dissipates. At steady state, the heat conducted into the fin at the base is equal to the heat lost to the environment by convection. This balance allows us to quantify the fin's thermal performance. Since the heat lost by the fin equals the heat entering at the base, we can take an indirect approach. It's often easier to calculate the base heat flow using simple conduction principles. Let's return to the long fin example. The temperature along the fin drops off exponentially, a nonlinear profile. To calculate the heat entering the fin at the base, we apply Fourier's law of conduction. What matters most here is the local temperature gradient, evaluated right at the base, where x equals 0. Since we're working with excess temperature, theta, we can express the gradient as d theta by dx. Putting it all together, we arrive at this boxed expression for the base heat flow. After all, if we know the local temperature along the fin, shouldn't we be able to compute convection point by point? Can we, instead, take a more direct approach and calculate Qfin directly? Does this approach give us the same result as using Fourier's law at the base? With the following derivation, we'll shed some light. Let's now dive in. Welcome back. During the analysis, we just saw the final result of integrating Newton's law of cooling. What do we observe from this? Comparing side by side with using Fourier's law, clearly the results are identical for the long fin example. Let's pause for a moment and think about what we've just seen. Can we always assume that the heat flow through the base is exactly equal to the heat transferred away from the fin's surface? Does this relationship always hold true? Try to picture at least two situations where it may not. That is, when would Qfin not be equal to Qbase? These are the kinds of cases where we need to take a different approach and apply, instead, the direct method of integrating convection. With the fundamentals in place, we're ready to assess the system-level performance. The total heat transfer from the heat sink comes from each individual fin, plus the contribution from the unfinned area. And finally, by adding everything together, you get the total heat transfer from your heat sink. Whether it's a single fin or a whole array, the principles remind us, good design starts with clear understanding. If you enjoyed this video, you may want to check out the following covering similar themes. Thank you for watching. Bye for now.